Hi, this is OzU Rover Team from Özyeğin University, Istanbul, Turkey. Since 2014, our team has been building rover prototypes. We are divided into 5 sub-teams to improve rover subsystems according to competition needs, which are locomotion, manipulation, autonomy, science and management. This year, we focused on improving our 7th generation rover Hope 2. We reduced the weight of the system by adding smaller Kestamit wheels. Thanks to the TPU-toothed wheels that we put around the rims, we increased the rover's traction. Our differential mechanism stabilized the rover during traversal. Rover was designed to be folded and easily transported. A multibody dynamic simulation was performed to analyze the rover's dynamic behavior. Before we begin manufacturing, we agreed on the best design specifications. Lithium polymer batteries are used to power the rover. The locomotion motors are powered by Talon SRX motor controllers with integrated PID controllers. An NVIDIA Jetson TX2 board transmits either autonomy softwares or operators' commands to these motor controllers over the CAN bus. Our manipulator has 5 degrees of freedom with a gripper used as an end effector. At the top of the end effector, a linear motor is placed to perform keyboard operations. With the help of inverse kinematics, the arm is controlled in Cartesian space. For each configuration given by the input joystick, joint angles are calculated and PID controllers are used at each joint to achieve the desired angle with minimal error. The servos on the arm are controlled with ROS through serial communication with the Jetson TX2. The DC motors are controlled through in-house made Arduino control boards. Arduino boards communicate with Jetson TX2 through serial communication. Each Arduino can control the motor current with an integrated motor driver, can read motor encoder and can switch the state of the motor brake. Stepper motors and linear actuator are controlled by motor drivers attached to separate Arduino Nano. 5V, 12V and 24V power lines are used for operation of the manipulator and its encoders. Our rover utilizes rotary encoders and a stereo depth sensor alongside GPS position feedback to produce stable odometry information. This year, we have developed an autonomous traversal algorithm called Safari, which stands for Sufficient Algorithm for Fast Rover Motion to use less computational resources while maintaining viewable and energy-efficient motion across road terrain. Different protocols were applied to increase the rover's operational safety. Our rover's current status is displayed in the activity indicator. In case of an emergency, we have also included an emergency stop button. When the button is pressed, the rover immediately stops. Science sub-team designed a unique onboard laboratory to detect the absence or presence of either extinct or extant life. Various sensors are used to gather information about carbon monoxide level, temperature, humidity level, wind speed, UV light intensity, and the barometric pressure. Using a drill, soil samples are taken from underneath of the surface and collected samples can be analyzed on board. Samples are chemically analyzed for potassium, phosphorus, nitrate concentrations, and pH value can be measured. An onboard microscope is used to view fossilized or living microbial communities. Hope to see you in Utah!